Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is sensors. Our objective is to examine sensors on an extremely introductory and general level. Later lectures will dive into all the gory details. However, in the interest of expediency, I thought I'd rush this content to the front of the line so we can start expanding our repertoire by incorporating sensors in some of our increasingly complex control system examples. Sensors, sometimes called transducers, are input devices related to switches. Switches, if you recall, come in many forms. Examples being electromechanical limit switches, pressure switches, temperature switches, rotational speed switches, and solid-state magnetic proximity switches, and more. Regardless of the type, all switches are binary or digital input devices, and that a switch can either be in its fully deactivated state or in its fully activated state, and never a little bit of both or halfway in between. Switches are fully on or fully off detection mechanisms only. Consider an electromechanical pressure switch with associated normally closed and normally open contacts. When exposed to pressure conditions below the adjustable set point, the associated contacts are in their deactivated states. As implied by their titles, the normally closed contact is closed and the normally open contact is open. When exposed to pressure conditions above the adjustable set point, the associated contacts switch their opposite activated states. The normally closed contact is held open and the normally open contact is held closed. When pressure falls below the reset value, the associated contacts return to their deactivated states. The normally closed contact recloses and the normally open contact reopens. If we were to plot this behavior on a graph of pressure versus time, the behavior would look something like this. Note the differential between the set and reset values, often known as hysteresis or span, is a desirable characteristic and prevents switch chatter when pressure is hovering at or near the set value. A pressure sensor or transducer, in contrast, is a related input device that, rather than switching between two mutually exclusive states at a given set or reset value, produces a voltage or current value proportional to the quantity being measured, in this case, pressure. As pressure rises, the output signal proportionally rises. As pressure falls, the output signal proportionally falls. Sensors, unlike switches, not only detect a phenomenon, but also measure and quantify it. This continuously variant analog output can be used by an electrically controlled system to appropriately respond to a range of input conditions. The schematic symbol for a sensor is pretty bland. Most sensors, regardless of type, are depicted as a box with a diagonal slash through it. Key to the operation of a sensor or transducer, as the name implies, is the process of transduction. Transduction is just a fancy title for the conversion of some physical phenomenon, like pressure, temperature, rotational speed, or position, into an electrical output. Transduction means vary depending upon the quantity being measured. A transduction mechanism for our example pressure sensor might be a pressure-sensitive plate that, when increasingly displaced or distorted by increasing pressure, produces an increasing voltage output. For our example pressure transducer, if we assume it to be operational inside a range from 0 to 1000 psi and capable of producing a 0 to 5 volt output, an input of 0 psi would correspond to an output of 0 volts, and an input of 1000 psi corresponds to an output of 5 volts. Assuming linearity, an input of 250 psi corresponds to an output of 1.25 volts, an input of 500 psi corresponds to an output of 2.5 volts, an input of 750 psi corresponds to an output of 3.75 volts, and so on. The ratio of the output and input ranges is sometimes known as the transfer function. Given this pressure sensor has a linear output between 0 and 5 volts for a range of 0 to 1000 psi, its transfer function suggests that this sensor produces 5 millivolts per psi. Given this transfer function, it is quite easy to determine the response given a particular input, or its input given a particular response. The transfer function is essentially a means of unit conversion. Allow me to demonstrate. Assuming an input pressure of 480 psi, we multiply it times the transfer function, oriented such that the units of psi cancel and only the unit of volts remain. In this case, the pressure sensor should produce an output of approximately 2.4 volts. Working this from the opposite end, assuming the pressure sensor is producing an output of 3.35 volts, we multiply this value times the transfer function, oriented such that the units of volts cancel and only the units of psi remain. In this case, the pressure sensor is most likely experiencing an input of 670 psi. While this example represents the process of transduction in its simplest form, in reality, this one-for-one exchange of psi for volts is a bit more complicated. Often transduction is a chain of conversion that ordinarily necessitates an external supply voltage continually power the internal electronics that make it possible. A more accurate depiction of a pressure transducer is a diaphragm that flexes under pressure to which capacitive plates are attached. As the flexible diaphragm varies the distance between the plates, the capacitive value changes and this capacitance value is converted to a proportional output voltage. In this case, pressure is converted to a distance is converted to a capacitance value, and capacitance value is converted to a voltage. Even this more sophisticated example of a multi-step chain of conversion is somewhat of a simplification, but the larger point is that when units are accounted for, psi comes in and volts come out. Additionally, it should be evident that if any step in the conversion process fails, for example, an obstruction that does not allow the diaphragm to flex, or a loss of supply voltage, the whole transduction process breaks down and the sensor's output is as reliable as your lazy lab partner's test results after a goofball binge. I should note that the actual output of various stages of the transduction process are often only very, very tiny electrical signals, and integrated amplifiers, devices that increase the output magnitude, are necessary to obtain usable output. This internal amplification is one type of signal conditioning. The acceptable range and format of a given sensor's output signal depends upon the construction of the sensor in question. The resultant output of a particular sensor can be a voltage signal in the range of 0 to 5 volts, 0 to 10 volts, negative 10 volts to positive 10 volts, or even a current signal in the range of 4 to 20 milliamperes. Depending upon the control system being employed, the output of the sensor itself might need to be externally conditioned such that it produces output with the correct format inside an acceptable range. Without going into unnecessary technical detail, these types of signal conditioners can also be thought as a means of transduction. If you have a pressure sensor that produces an output from 0 to 5 volts, but your system requires input from 0 to 10 volts, a signal conditioner can be used to reformat this sensor output into something usable by this system. In this case, the signal conditioner is basically a voltage-to-voltage converter that takes a 0 to 5 volt input signal and reformats it into a proportional 0 to 10 volt output signal. Another example of a signal conditioner would be a current-to-voltage converter that reformats a 4 to 20 milliampere current output signal of a proportional valve spool position feedback into a voltage signal inside the range from negative 10 to positive 10 volts. Note this signal conditioner allows not only changes in magnitude and format, but also polarity. For the purposes of this lecture, we're ignoring the internal construction of these signal conditioning apparatuses and treating them as magic boxes. Signal conditioners may be separate external entities, or they may be integrated into a sensor or the system itself. It should go without stating that if sensor output is not properly conditioned consistent with a control system's expected input, extremely undesirable behavior will occur. Returning to the discussion of acceptable input and output ranges, realize the control system expecting a continuously variant 0 to 10 volt analog input signal largely does not care what this voltage signal represents. 0 to 10 volts could represent 0 to 100 psi, or just as easily 0 to 5000 psi. The continuously variant 0 to 10 volt analog input signal is a pilot voltage signal only. This is to suggest that a sensor and system must have some prior agreement as to what this pilot voltage signal represents, and the sensor must be calibrated inside this appropriate range. Two important points exist within the sensor's transduction range, notably the zero and the span. The 0, as the name implies, is the minimum input value that results in minimum output signal. The span is essentially the opposite, being the maximum input value that results in maximum output signal. The 0 and span of a sensor are often adjustable quantities, and proper calibration of a system must account for both these adjustments. Assuming our example pressure sensor is operational inside a range of 0 to 1000 psi and produces an output signal between 0 and 5 volts and has both an adjustable 0 and span, the calibration process is quite simple. With minimum operating pressure, in this case 0 psi, applied to the pressure port, the 0 potentiometer is adjusted such that the sensor produces 0 volts. With maximum operating pressure, in this case 1000 psi applied to the pressure port, the span potentiometer is adjusted such that the sensor produces 5 volts. As previously, the full range of 0 to 1000 psi is represented by 0 to 5 volts, and the linear transfer function is 5 millivolts per psi. Given this sensor output is conditioned by a voltage-to-voltage converter, the system receives the required 0 to 10 volt range. This might not seem earth-shattering to you until you realize this calibration process means nothing at all. Given another system with a minimum pressure of 50 psi and a maximum of 500 psi, one could also adjust the full range of this pressure sensor output to encompass only these values. With minimum operating pressure, in this case 50 psi applied to the pressure port, the 0 potentiometer is adjusted such that the sensor produces 0 volts. With maximum operating pressure, in this case 500 psi applied to the pressure port, the span potentiometer is adjusted such that the sensor produces 5 volts. In this scenario, the 450 psi differential between 50 to 500 psi is represented by 0 to 5 volts. The linear transfer function is approximately 11.1 millivolts per psi and must include a 50 psi offset. Again, given this output is conditioned by a voltage-to-voltage converter, the system receives the required 0 to 10 volt input. In both scenarios, the unconditioned output of the pressure sensor is still 0 to 5 volts. The only difference being that the output represents different levels of magnification. For our first scenario, 0 to 5 volt output represents the full 1000 psi range of the pressure sensor, whereas the second scenario, the 0 to 5 volt output represents only a 450 psi. While the first scenario does represent an increased range, the second scenario represents increased sensitivity inside a smaller range. Depending upon the system requirements, one scaling method might be preferred over another. This bears repetition. You can calibrate a sensor's 0 and span any way you want. And if you do it wrong, your system won't work as intended. Regardless of the method employed, the same pressure sensor is being utilized, and realize it is still hard limited to 1000 psi. If either system ever experienced a pressure spike above 1000 psi, the pressure sensor could be irrevocably damaged, an example being the permanent distortion of the diaphragm to maximum deflection. In this case, the unconditioned sensor output would continuously flatline at 5 volts and cease to report any usable data. Moving on. For want of an initial example, I've inadvertently let pressure sensors kind of steal the show. Let's switch discussion to other representative examples of sensors or transducers commonly employed in electrically controlled systems. Again, I am keeping this initial discussion extremely general in nature, do not plan to go into detailed specifics. Other physical phenomenon can also be detected and measured using sensors that produce a voltage or current signal proportional to the measured quantity. Examples being rotational speed sensors, position sensors, and temperature sensors. Rotational speed sensors come in numerous forms, two of the most basic being tachometer generators, and for lack of a better term, something I'm calling a frequency to voltage converter, of which there are numerous different incantations. A tachometer generator is quite simply a magnet and a coil. One member of the pair is attached to the rotating shaft. Let's assume that this is the magnet, and the other member is fixed and placed in close proximity. Let's assume that this is the coil. Tachometer generators operate on the principle of Faraday's law of electromagnetic induction, which states that a voltage will be induced across the terminals of a coil in proportion to the number of windings and the rate of change of magnetic flux. In practical terms, this means spin the magnet slow and you'll get a small voltage, and spin the magnet fast and you'll get a large voltage. This is the one scenario I can think off the top of my head in which the transduction process really is kind of a cartoonish one-for-one exchange of RPMs for volts. The other common type of rotational speed sensor, believe it or not, uses a simple switch as its detection mechanism, and the output of this switch is sent into a frequency to voltage converter. The switch at the front end of a rotational speed sensor can use several different detection methods. Examples being a magnetic proximity detector that alternatively registers the presence or absence of a magnetic tag on the rotating shaft, or an optically based detection mechanism like a through beam or retroreflective photoelectric eye. In either case, every time the shaft revolves, the magnetic proximity switch or photoelectric eye is activated once per revolution. If the shaft spins slowly, the periodic activation and deactivation of the switch produces a low-frequency pulsed signal. If the shaft spins quickly, the periodic activation and deactivation of the switch produces a high-frequency pulsed signal. The next stage of a rotational speed sensor is the frequency to voltage converter, which simply outputs a voltage proportional to the input frequency. Low frequency input results in a low voltage output. High frequency input results in a proportionally high voltage output. I promised I wouldn't do this, but to satisfy curiosity, when we break open the frequency to voltage converter, we see three subsystems that work together to perform the frequency to voltage conversion. Principally a timer and a counter. The third subsystem is a digital to analog converter, which I'll explain in a moment. The timer basically establishes a repetitive sample window, let's say 5 seconds. During 5-second window, the counter counts how many pulses occur. If the counter experiences 150 pulses in 5 seconds, it can be demonstrated using this thing called math that the rotational speed is 1,800 RPM. After 5 seconds, the timer clears the counter and enables it again. If the counter experiences 125 pulses in 5 seconds, it can be demonstrated that the rotational speed is dropped to 1,500 RPM. After 5 seconds, the timer clears the counter and enables it again, and so on. The third subsystem, the digital to analog converter, is taking the digital representation of counter output and matching it to an analog scale established when the rotational speed sensor was calibrating using the zero and span adjustment. Assuming 0 to 3600 RPM input perfectly corresponds to a linear 0 to 10 volt output, we can see that the transfer function is roughly 2.8 millivolts per RPM and necessitates no offset. The first sample will therefore produce a 5 volt output, and the second sample a roughly 4.2 volt output. When this process is repeated over and over, every 5 seconds the analog output of the rotational speed sensor is updated, producing a continuously varying analog output voltage signal proportional to the rotational speed of the shaft. More sophisticated rotational speed sensors will obviously perform this on a more frequent basis, using extremely small sample windows. The disadvantage of a rotational speed sensor as currently implemented is that it cannot distinguish between clockwise and counterclockwise rotation, since the single clockwise rotation would trigger the switch once, as would a single counterclockwise rotation. With very little effort, a rotational speed sensor can also indicate not only magnitude, but also rotational direction. Consider a system that employs two tags, A and B, ever so slightly offset from each other on the shaft. If stationary switch A and switch B are in line with one another, and A is triggered before B, the shaft is obviously rotating in one direction. If switch B is triggered before A, the shaft is obviously rotating in the other direction. Such a system measuring both rotational speed and direction can represent the two related quantities using a couple different formats. First, speed and direction can be represented using two separate pieces of data. Rotational speed magnitude can be represented as previously using a proportional voltage signal. Direction can be independently represented as a digital or logical value. Using our previously scaled rotational speed sensor, given an input of 1800 RPM clockwise, the sensor would output 5 volts at the analog speed output and a logical 1 as indicated by the lack of an overbar at the direction output. Alternatively, given an input of 1800 RPM counterclockwise, the system would output 5 volts at the analog speed output and a logical 0 or counterclockwise as indicated by the negation overbar at the direction output. Alternatively, related speed and direction quantities can be represented using a single analog output, where polarity of the voltage is indicative of direction. An example using our previously scaled rotational speed sensor would be positive 5 volts for clockwise rotation at 1800 RPM and negative 5 volts for counterclockwise rotation at 1800 RPM. Alternative rotational speed measurement methods exist, including more robust relative encoding and incredibly sophisticated absolute encoding, which assigns each angular position on the shaft a unique digital address. We'll examine the details behind relative and absolute encoding methods in much later lectures. Although ostensibly a rotational speed measurement, rotational speed sensors can be employed with very little modifications to perform measurement of other physical phenomena, examples being fluid velocity and flow rate. Consider an anemometer, a means of measuring wind speed or fluid velocity. An anemometer is essentially a rotational speed sensor. As wind speed increases, the anemometer registers more revolutions per sample window and outputs a voltage signal proportional to wind speed. Wind speed is critical information for weather stations and the efficient and safe performance of modern horizontal axis wind turbine generators. Alternatively, consider one type of flow meter, which immerses a paddle wheel or turbine blades in a liquid or gas. If rotational speed is proportional to fluid velocity, the flow rate, a measure of volume per unit time, can be calculated using the cross-sectional area of the pipe through which the fluid flows. Like I said previously, the transduction process is often a game of telephone, where one quantity must undergo a series of complicated transactions before it ultimately outputs a voltage or current signal proportional to the measured quantity. It goes without stating there is often some complicated math, a degree of computation, and demanding electronics knowledge that goes into the design and construction of a sensor that I am purposely overlooking in the interest of brevity. Moving on, let's examine representative examples of position sensors. Simple position sensors can be best conceptualized as a potentiometer and a voltage divider arrangement, where displacement affects the observed voltage at the central terminal. Consider a 10 kilo-ohm potentiometer with a 10 volt differential across the A to C terminal. When the central B terminal is adjusted to 75%, such that 2.5 kilo-ohms of the available 10K appears between A to B terminals, and the remaining 7.5K appears between the B to C terminals, it can be quickly demonstrated using the voltage divider rule that the voltage drop across the A to B terminals would be 2.5 volts, and the voltage drop across the B to C terminals would be the remaining 7.5 volts. If the central terminal was displaced midway, it can again be demonstrated using the voltage divider rule that the voltage drop across the A to B terminals would be 5 volts, and the voltage drop across the B to C terminals would be the remaining 5 volts. For those requiring assistance with the voltage divider rule, please check out the DC voltage divider rule lecture available at the Big Bad Tech channel. Ultimately, as the position of the potentiometer central terminal is physically varied, so would the voltage output. The potentiometer output has in effect become a sliding scale representative of linear displacement. As primitive and crude as this method seems, it's effective. Consider a potentiometer with a rotational adjustment knob to which is attached a spring-loaded coil of wire. If the wire is attached to the tip of a hydraulic cylinder rod, as the rod extends, it unwinds the cable and rotates the potentiometer adjustment knob. Conversely, when the rod retracts, the spring-loaded coil reels in, returning the potentiometer adjustment knob to the start position. Voltage at the output terminals would therefore be proportional to linear displacement. At commissioning, the zero and span of this potentiometer-based position sensor would need to be adjusted for full retraction and full extension. Assuming linearity, and let's say a cylinder with a 10-inch travel length, just to keep the math easy, the 10-volt output range is broken into 1 volt per inch chunks. The problem with this contrivance is that it's riddled with inefficiency and mechanical problems. The wire could stretch over time, the reel could bind, or any number of tolerance issues could develop, all servicing to decrease the accuracy and response of this system. Significantly more sophisticated linear position sensors exist, including linear variable differential transformers, sometimes called linear variable differential transducers, both conveniently abbreviated LVDT, and magnetorestrictive waveguides. We briefly introduced the LVDT when we examined the proportional valve, where it was employed as a spool position sensor. However, we kind of shortcut the details. An LVDT consists of a magnetically permeable core that slides inside a hollow bore. Around the hollow bore are wrapped the windings of a primary and 2 secondary coils of a transformer. When the primary coil is excited by a high-frequency AC source, an output voltage is observed on the secondary coils via electromagnetic induction. Assuming a perfectly centered core, there would exist no differential between the 2 secondary transformers. However, if the core is displaced towards one end or another by an object to which it is mechanically coupled, whether this object is a tiny spool inside a proportional valve or the rod of a large hydraulic cylinder, there would exist a differential proportional to the core displacement. Signal conditioners internal to the LVDT would format the differential as an analog representation of linear displacement. Another common method of linear position measurement makes use of a magnetorestrictive waveguide. Using this extremely cunning method, a position magnet is mechanically coupled to a linearly moving object, and this position magnet floats or slides along a waveguide. As the object moves left or right, the magnet comes along for the ride. Regular tiny pulses of current are sent down the waveguide. When the current pulse, itself carrying a radial magnetic field, reaches the position magnet, there is an interaction between the 2 magnetic fields that produces a torsional or twisting strain in the waveguide. The torsional strain pulse propagates the length of the waveguide at ultrasonic speed. At the receiver end, the pulse is converted to an electrical signal. Given the ultrasonic pulse is traveling at a regular and predictable speed, the time span between the generation of the current pulse and the receipt of the ultrasonic echo is a highly accurate representation of the linear displacement of the position magnet. Again, with subtle alterations in deployment, these methods of linear position transduction can be employed to measure other quantities. Consider a level sensor making use of a magnetorestrictive waveguide where float is coupled to the position magnet. As the level in the tank varies, the float slides the position magnet up and down the waveguide, and the sensor outputs an analog value proportional to the quantity of liquid in the tank. Another alternative application of a position transducer is that of vibration measurement. Consider an extremely minute yet incredibly precise position transducer, as whatever the vibration sensor is attached to, be it a gearbox, bearing, or frame, bounces up and down due to misalignment, lack of lubrication, or some other influencing factor, the vibration sensor measures this displacement. One last quick example of transducers, temperature sensors, before we move on to another topic. Several different types of temperature sensors exist, 2 of the most common being RTDs and thermocouples. RTD stands for Resistance Temperature Detector. The principle of RTD operation is positive temperature correlation, and that if you heat something up, its resistance increases. RTDs are often made of platinum because the proportional variation of resistance as a function of temperature is linear, precise, and repeatable. The RTD is in effect a thermistor, a resistor that varies as a function of temperature. Using the principle of Ohm's law, perhaps you've heard of it, observed voltage and current properties relay temperature variations. Thermocouples are another type of temperature sensor that operate on a totally different principle, that principle being the thermoelectric effect. A thermoelectric device generates a tiny yet predictable voltage proportional to the temperature differential across it. One end of a thermocouple, the reference or cold end, is maintained at a constant temperature, and the other end, the measuring or hot end, is exposed to the process being measured. Via the onboard signal conditioning electronics, a proportional voltage or current signal is generated representative of temperature. I feel like I could go on like this all day with more and more examples of physical phenomenon being represented via various transduction methods, but I've got to draw a line somewhere if we want to keep this lecture manageable and introductory in nature. Long story short, a sensor is not only a detection mechanism, but also a means of measuring a quantity. Via the transduction process, the physical phenomenon being measured, whether it is pressure, rotational speed, wind speed, flow rate, position, level, or temperature, is represented as a proportional voltage or current quantity. By adjusting the zero and span, an operational range can be established and appropriately scaled for the particular application. Left unasked until now is the very valid quandary. Why is this proportional representation of a measured quantity so important that I'm sitting here watching this lecture instead of playing with my dog? The answer is many-layered, and true appreciation of analog representation of both input and output will come in time. However, I can summarize its significance with a couple important applications, namely data recording and process control. A very simple and straightforward application of analog sensors is often the very real need to record data for the needs of some process or for the purposes of troubleshooting should a fault occur. Consider a modern horizontal axis wind turbine generator with numerous sensors relaying data to the control system. Rotational speed sensors measure the rotational speed of both the low-speed main shaft and the high-speed shaft. An anemometer measures wind speed. Temperature sensors measure the temperature of the gearbox and generator. Vibration sensors monitor vibrations of the gearbox. Angle transducers measure the pitch angle of the blades. Integrated current transformers and voltmeters measure input and output electrical quantities, and so on. On a continual basis, the control system records and stores this data relayed by the sensors. Additionally, this data can be transmitted to a remote supervisory control and data acquisition network. Should a fault occur, either an overcurrent event, excess vibration, or overspeed condition, the turbine control system can initiate a safe shutdown. Having access to all the data at the time of a shutdown, a technician, remote operator, or the automated system itself can make a decision to resume operation or initiate a call for service. Additionally, historic trends can be captured and analyzed using the accumulated data. For example, if the vibration sensor on the main shaft bearing indicates an increasing trend, a technician can be dispatched to perform inspection or preventative maintenance before the issue becomes a deal breaker. This type of predictive maintenance would not be possible without a sensor that not only detects a quantity, but also measures and quantifies it. I should note with delicious irony that the analog data relayed by sensors is stored and sometimes transmitted in a digital format, since computers kind of struggle with analog data. Computers find packages of digital data easier to transmit, store, process, and more resistant to electrical noise. A detailed understanding of digital to analog conversion and vice versa is not essential to our current level of understanding, but as an example, the analog value of 10 in base 10 number system can be represented using regular 8-bit binary or base 2 system as 00001010. Those interested in binary numbers are encouraged to check out my lectures on digital electronics. Regardless, analog to digital and digital to analog converters make this conversion process from one format to another a possibility. Another important application made possible with sensors is that of process control, the most basic aspect being that of comparison. The end goal of most systems is to produce some desired output, often called the process variable. This could be the exertion of a given amount of force over a certain distance, keeping the rotational speed of a shaft inside a given range, maintaining liquid level in a tank constant, holding or moving an actuator and applied load to a certain position, keeping the temperature in a room constant, or some other measurable result. This ideal result is known as the set point. Two general classes of controllers exist for such systems: open loop and closed loop control. An open loop control system is a means of process control that does not use feedback to determine if resultant output has achieved the desired goal. This means that the system acts upon but does not observe the resultant output of the process it is controlling. Consequently, while simple and relatively inexpensive, an open loop control system cannot automatically correct any errors, nor can it compensate for disturbances. A closed loop controller, in contrast, is one that does use sensor feedback to determine if resultant output has achieved the desired goal. This means that the system not only acts upon, but also observes the resultant output of the process it is controlling. Consequently, a closed loop controller can compare the output process variable with the desired set point. If a differential between the output process variable and set point exists, an error in excess or detriment is registered, and the closed loop control system can automatically correct any errors and compensate for disturbances. Keeping with our earlier wind turbine generator example, the generation process is most efficient inside a range of rotational speeds. Given wind is not a controllable quantity, a turbine does this by pitching or changing the angle of the blades, either spilling excess air or moving them towards a more aggressive attack angle. Assuming a set point of 1850 RPM at the high-speed shaft, a closed-loop controller can be used to maintain the high-speed shaft rotational speed close to this value despite variations in wind speed. Assuming the rotational speed sensor produces a 0 to 10 volt output linearly proportional to speed inside a 0 to 3600 RPM range, it can be demonstrated that the transfer function is approximately 2.8 millivolts per RPM, and that a value of 1850 RPM corresponds to approximately 5.1-ish volts. Assuming the high-speed shaft really is at 1850 RPM, both the set point and feedback are at 5.1 volts, and the differential or error between them is 0 volts. No error signal is sent to the controller, and no adjustment to the wind turbine is warranted because rotational speed is exactly where we want it. Let's say a strong gust of wind strikes the turbine and the rotational speed of the high-speed shaft briefly increases to 1900 RPM. The feedback signal rises to approximately 5.3 volts, and there exists a differential of approximately negative 0.2 volts in excess of the desired set point. Note the polarity of the set point and feedback at the point of comparison, often called the summing junction. The set point is positive and the feedback is negative. When the feedback is in excess of the set point, the error is negative, meaning that the system actuators need to lay off the gas in an effort to reduce the output. Noticing not only the magnitude of the differential, but also the polarity, the controller can signal the blades to pitch back and spill some wind. Rotational speed drops and eventually stabilizes at 1850 RPM, such that there exists no differential between the set point and feedback. Coming at this from the other end, let's say the turbine experiences a momentary lull and the rotational speed of the high-speed shaft decreases to 1800 RPM. The feedback signal drops to 5 volts and there exists a differential of approximately positive 0.1 volts. Again, accounting for polarity of the set point and feedback at the summing junction, the error is positive, meaning that the system actuators need to step on the gas in an effort to increase output. Noticing not only the magnitude of the differential, but also the polarity, the controller can signal the blades towards a more aggressive attack angle. Rotational speed increases and eventually stabilizes at 1850 RPM, such that there again exists no differential between the set point and feedback. By continually monitoring and comparing the process variable through sensor feedback with the set point and adjusting actuators to respond to changes positively or negatively, the closed-loop controller keeps the rotational speed inside this desired range and the generation process as productive and efficient as possible. I've obviously simplified this process, neglecting numerous influencing factors such as wind and yaw direction. However, the larger principles are pretty accurate. The larger take-home point of this lecture, focusing on an introduction to sensors, being that a closed-loop controller would not be possible without a sensor measuring the resultant output process variable. Sensors capable of producing continuously varying analog representations of the quantity being measured make this level of process control a workable reality. Alright, that's about it for our quick introduction to sensors. No, we did not cover everything, and I've made some obvious sweeping generalizations, but we did gain general knowledge of sensors and the transduction process, and at least a basic knowledge of how they are employed in a control system. As time and occasion allow, I hope to examine specific sensors and control systems in greater detail. Until then, this will serve as at least a general introduction. In conclusion, this lecture took a brief introductory look at sensors or transducers. We examined various methods of transduction for pressure, rotational speed, fluid velocity, flow rate, position, level, vibration, and temperature. Additionally, we discussed transfer functions and the process of adjusting the zero and span of a particular sensor. Finally, we examined how sensors are employed in closed-loop controllers and how closed-loop controllers can automatically correct any errors and compensate for disturbances. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.